Okay, good morning. It is a great opportunity for me to share to you regarding the equilibrium. Today, we're gonna discuss regarding the Le Chatelier principle. Um, Le Chatelier's yeah principle. So it is actually the integral part of the equilibrium that we learn in AS level, right? So before I begin the discussion, I would like to share to you the lesson objective. Yeah, lesson objectives of this topic is the first and foremost, by the end of this meeting, you should be able to describe the equilibrium principle, yeah, equilibrium principle, in terms of the in terms of the process of Haber. So later on we will discuss regarding the Haber process. All right, and the second thing that we like to discuss is basically you should by the end of this meeting, yeah, you should be able to explain the value or the effect of temperature on the value of Kc. Yeah. The third objective that you need to uh, obtain by the end of this lesson is basically you should be able to calculate, yeah, calculate the Kc and Kp. So how they differ, I will tell you later on. Okay. So all right. So other than this, last but not the least is basically you will be able to discuss, yeah, discuss the um, factors, yeah, that affect the um, equilibrium, yeah. So that's actually the several things that we'll discuss over the course of this lesson. Let me embark with the first principle, yeah, the first learning objective. So the equilibrium is basically is symbolized by the forward and backward arrow. Yeah. So it says here, when a system's in equilibrium is disturbed, the positions of equilibrium will shift to cancel the effect of the change so that equilibrium is re-established. All right. So um, that means, for example, I give an example. Yeah, sorry. One example is basically the reactions between nitrogen gas plus hydrogen gas to give ammonia. All right. And then if we read this chemical reaction, so you should be able to balance the coefficient so that the number of atoms on the left hand side equals to the right hand side. And then based on this process, right? So we call this one Haber process. Yeah. So this Haber process is basically exothermic reaction. Yeah. So this is the exothermic reaction where the energy is given out from the system to surrounding. All right. So the principle is basically if we able to alter the compositions in terms of concentration, in terms of the pressure, all right, on the left hand side, or it could be volume, then it will affect the percentage yield of ammonia or the product. All right. Now, if I may progress, all right. So definitely we can actually uh, consider that these all substances on the left hand side is called as a reactant. All right. And then the one that we have on the right hand side is called as a product. Yeah, so the reactant and products, right? So if in case we have this arrow, which is the Fora reaction over the right hand side, the one that I put in pink, we call this one right hand side. So I just use RHS, and then here I have a left hand side or LHS. So definitely this is the process of equilibrium, right? So the thing that you need to remember is number one, the concentration. Okay, so this is actually something that you need to ponder. The concentrations, or I just symbolize of the bracket, right? So the concentration of nitrogen and hydrogen and of course ammonia at equilibrium. So let me just very clear on this. At equilibrium is actually the same, right? So that's why I put in the other color is same. So this is the principle of the equilibrium, all right? So the one that I put inside this rectangle box, yeah? So the principle, concentrations of nitrogen and concentrations of hydrogen is equal to concentrations of ammonia, right? Okay, next is you should be able to check that the state symbol that we use here is supposed to be either gas or liquid, yeah, or aqueous. Because, all right, so because whenever we have the reaction that includes the equilibrium, and in that particular reactions you have a solid state, then you should able to ignore this one. So this one should be ignored. Yeah. So the solid state is basically is not applicable for the calculations of equilibrium, right? So that's the first thing that you need to remember when we discuss regarding this the equilibrium principle. All right. So that means we already discussed the first point of our learning objectives. Now let me progress to the second part of this. Yeah. So now let's discuss. Excuse me. Let's discuss regarding the effect of temperature, right? So the effect of temperature is also one of the considerations on the equilibrium. Yeah. So using the same, what you call this one, using the same reaction. So nitrogen plus 3 hydrogen gas, okay, to give 2 molecules of ammonia. All right. So um, whenever we discuss regarding the effect of temperature, you should be able or you should be aware on the sign of this delta H on the right hand side. So why is it so crucial? Because this um, this sign basically, right? So the nature of this reaction will determine where the equilibrium will be shifted. Yeah. So in this case, because the delta H is less than 0, so that means this reaction is categorized as a exothermic reaction. All right. So as I said earlier, exothermic reaction is the reactions where the energy is given out from the system and surrounding. So in case you still in doubt, in order to determine which one is the system, which one is the surrounding. So I will write the box shows you to show you, right? So we have the differentiations between system and surrounding. All right. Okay, so we have a system and surrounding. Definitely surrounding. Okay, so definitely the system is basically the chemical reaction itself. So it is actually the chemical reaction itself. So for example, in this case, it's actually the reactions between nitrogen and hydrogen to give ammonia. So the system is basically the nitrogen, hydrogen, and ammonia. All right. So that means, for example, if you conduct this experiment using the, for example, beaker glass or polystyrene cup. All right. So let's say I have polystyrene cup, and then I insert, for example, thermometer. All right, so for example, I put thermometer, and then I have this gas, for example, right? So definitely I will be able to observe that the temperature of this thermometer increases. So the temperature increases because the energy is given out from the reactions of nitrogen, hydrogen to give ammonia from the system goes to surrounding. So the surrounding is basically the thermometer. So the boundary of surroundings basically it's something that greater than the or 1 nanometer away from the system is called surrounding. So there's like interface between the system and surrounding that you need to be able to uh, check which one is the system, which one is surrounding, right? So air out of these or anything greater or beyond the nitrogen and hydrogen is called surrounding, all right? Now, therefore, there are two things that you need to consider regarding this one, yeah, regarding the effect of temperature. Number one, it is crucial for you to remember that if you increase temperature, so meaning we increase the temperature, then equilibrium shifts to the side of endothermic. All right, so I just put here is actually endo. All right, so it shifts to endo. Okay, now in case you have, for example, if you lower the temperature, right? So lowering temperature for this one, so it equilibrium shifts to the side of exo. All right, so that's actually the first thing that you need to know whenever we adjust the temperature. So that means if we check this reaction, so if you increase the temperature, then it is actually poor decisions in order to gain more ammonia, because in this case, right, in this case, you're gonna uh, get less number of ammonia because basically the equilibrium shifts to the left hand side. Why do I say that? All right, so I need to be very clear because whenever you receive this reaction, the one that I put here in the box, so you should be able to interpret this reaction as the four reactions or the right hand side reaction as an exothermic. So meaning if you lower the temperature or if you wish to get more, right, or to produce more ammonia, then the thing that you need to do is by lowering the temperature. So you should be lower temperature. That means the equilibrium shifts to the right hand side, making the percentage yield of ammonia increases. That's how you do it. All right. So I already discussed the second point here. The third point that I would like to discuss is actually the calculations of Kc and Kp. All right. So suppose we have ice. All right, so ice we have initial. So ice stands for initial, change, and equilibrium, right? So definitely we have the specific concentrations of nitrogen, hydrogen, and ammonia. But then since ammonia is zero or there's no ammonia in the beginning, so we can actually put this one as a 0. So right, for example, I have 2 moles of nitrogen, and then for example 1 mole of hydrogen, right? So I need to be very clear on heat in this unit. Okay, so I would like to ask, and then for example, if I put these two gases in the vessel, then what is the Kc? Yeah. So for example, the volume is 1 dm cube. All right. So what is the molecules one as a Kc? Now, Kc stands for the equilibrium constant. Yeah. So equilibrium constant in terms of concentration. So Kc is actually equilibrium constant, okay, in terms of concentration, while Kp is actually equilibrium constant in terms of pressure, right? So we're gonna discuss this one. So in short, so for example, in this case, hydrogen is limited. So meaning, for example, sorry, in this case, for example, the amount of hydrogen is less than amount of nitrogen. So then I still have 0.5 mole of hydrogen. And then for number of nitrogen is actually the mole ratio is applicable, right? So we have one coefficients of nitrogen, so 1 over 3 times 0.5. Then definitely, okay, so 1 over 3 times 1 over 2, you have 1 over 6. So you're going to have around 1 over 6 mole. All right, so to uniform, this one I just put half. So we can have a consistency in terms of the number, right? So, okay, so meaning I have a 2 minus 1 over 6. So basically, it's actually 12 over 6 minus 1 over 6. I have 11 over 6. So I have 11 over 6 mole over here. So equilibrium is actually the difference between initial and changes. So I is actually initial, C is actually change, and E is actually at equilibrium. All right, equilibrium. So that means the concentrations or mole of all substances that we have here is actually the difference between initial and concentration. And of course, we have the ammonia here because the coefficient is 2 and the coefficients of hydrogen is 3. So that means that we have 2 over 3 times half. Definitely, you have 2 over 6, right? So which is 1 over 3. So now I have 1 over 3 mole over there. All right. Then, therefore, I can remove. Yeah. So I think I need more space over here. Okay. So in order to calculate the Kc, all right, so what shall I do is basically to find the ratio. Yeah. So Kc for this one is actually the concentration of the product divided by concentrations of the reactant raised to the power of its coefficient. Okay, again, the concentrations of product raised to the power of its coefficient divided by the reactant. All right, so because concentration is actually mole over volume, but the volume here is basically what equals 1 dm cube, so definitely there's no change, right? So divided by, I have 1 over 2 times power 3. So this one is power 2 because I have 2 over there and then 3 over there, and then I have 11 over 6. So then you can actually get this one. And of course, the unit, yeah, so definitely you can use your calculator to get this one. But the most important thing is actually the unit. So here you have a unit of mole square dm minus 6. At the bottom is actually you have mole power 3 dm minus 9, and then mole dm minus 3. So definitely at the bottom side you would have mole power 4 dm minus 12. So you can actually cancel here, cancel, 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 cancel. So now you have the leftover would be mole minus 2, all right, and then dm minus power 6. Yeah, so that's how you do it, the Kc. All right, so what about Kp, right? So Kp can be um, calculated using the value of partial pressure. So there will be different what equals one discussion for this. So let's say instead of I have a volume, now I have pressure. The total pressure, for example, 12 atm, right? Now, in order to calculate Kp, it is actually most likely similar to the one that we have earlier, but then you should be able to get this one. P of ammonia power 2 divided by P of hydrogen power 3 and P of nitrogen. But then how about P? The pressure of nitrogen is actually the ratio of this one. Okay, so 1 over 3 divided by 11 over 6 uh, plus 1 over 2 plus 1 over 3. So that's actually how you do it. And then that's actually partial pressure of ammonia. Then what about partial pressures of hydrogen? Basically, it's actually half divided by 11 over 6 plus 1 over 2 plus 1 over 3. What about partial pressure of nitrogen? Actually, 11 over 6, right? So, sorry, 11 over 6 divided by 11 over 6 plus 1 over 2 plus 1 over 3. Now, and then all this one will multiply by 12. Divided by 12 and it's by 12. So all the numbers will be imputed in this one. Then you can get Kp. All right. I think that's all because I already explained also the factors effect of equilibrium, which is the concentration, pressure, and also volume. I think that's all. Thank you for attending this class and see you again in the next class. Goodbye.